Hi, my name is Dennis. I'm an XRPL Core Developer for XRPL Labs, and today we're going to be talking about the SQL database. So our agenda, we're going to cover the SQL database overview and purpose. We'll go into the architecture and components, the database schema design, connection management and configuration, data storage and retrieval process, and integration with application architecture. So first, what is the SQL database? It is the primary data storage layer for the XRPL node historical data. It is a relational database interface for persistent storage of ledgers, transactions, and account history. Its core responsibilities are to store and retrieve ledger data across node restarts, maintain transaction history for account queries, support historical data analysis and reporting, and provide efficient access to blockchain state history. Some of the key benefits: durability, the data survives node crashes and restarts. It's got query flexibility using SQL. It's got space efficiency for optimized storage and performance for indexed access for fast lookups. The architecture of the SQL database is a relational interface. So it's an abstract class that defines the database operations. It provides a consistent API across different database backends. The SQL database implication is a concrete implementation for SQLite. It inherits the SQL database class, and it manages actual database operations and connections. The database con class is a thread-safe connection wrapper. It handles SQLite pragma settings and manages the connection lifestyle with configurations. So the database schema design, it's got two primary databases, the ledger database and transactions database. It's a modular design for optional transaction tables via configuration, and a normalized schema for efficient storage and query performance. The ledgers table stores ledger header and metadata. It's indexed by the ledger sequence number and contains ledger hash, timestamp, and state information. The transactions table stores individual transactions data, links to the parent ledger via the foreign key, and contains the transaction hash, type, and serialized data. There's also an account transactions table, which maps the accounts to their transaction history, enables efficient account-based queries, and supports pagination for large result sets. So connection management and configuration, we set the configuration in the RippleD configure file. This allows for thread safety, so multiple threads can safely access the database. Connection pooling prevents resource conflicts, and proper locking mechanisms for concurrent access. The pragma settings are SQLite specific optimizations, performance tuning parameters, and consistency and durability settings. And the connection lifestyle has an automatic connection establishment, proper cleanup and shutdown, and error handling and recovery. Next, we have data storage and retrieval concepts. So the ledger storage is the sequential ledger data storage. It provides efficient range queries by ledger sequence, and it also allows for metadata indexing for quick lookups. The transaction storage allows for a hierarchical storage under parent ledgers, account-based indexing for history queries, and optimized serialization formats. So how does this integrate with the application architecture? First, we initialize the database. So we set the database during node startup, the schema validation and migration, and we establish the connection pool. For ledger processing, we store new ledgers as they are validated. We update the transactions tables with new data. For the query service, we support RPC commands requiring historical data, account history queries, and ledger range retrievals. The SQL database interface is a foundational component in modern software systems, providing a structured and reliable way to interact with relational databases. Thank you for watching.